All right, welcome back. This is our last lesson for magnetism and therefore our last lesson for electromagnetism, chapters 7 and 8. Tomorrow I will be posting a Explore Learning gizmo for you to work on. So that'll be Wednesday. And then on Thursday, I will post an Google form quiz for chapters 7 and 8. And you can use Thursday and Friday to work through that. I'll post a new video Friday, but that'll be for Monday. But if you want to work ahead, start the new unit, which will be modern physics. It's a combination of the wave nature of light and modern physics. That's our last unit. It is a big unit, but we're on our last unit. So no worries, we'll get through everything with plenty of time. And just keep looking at the Google Classroom for new information as it comes out. Right, so Ampere's law. Ampere's law is named after Ampere. I call him another absent-minded genius because he was actually invited to have dinner with the Emperor Napoleon. He forgot about it and then stood him up. That's all right. He's a physicist. He can do that. Moving on. So we learned that if we have a current moving through a straight wire, we get a magnetic field. And we learned the right-hand rule to actually determine the direction of that magnetic field. Today what we're going to do is determine the strength of that magnetic field. Now, experimentally, we know it's proportional to current. The greater the current you have flowing through that wire, the greater the magnetic field. We also know it's inversely proportional to the distance from that conductor. Not the distance squared, the distance. Why is it distance and not distance squared? Well, think of it this way. If you're looking at something like gravity or the electric field strength moving out from a point charge, you're moving outwards in 3 dimensions. And the surface area of that sphere, if you were to calculate the surface area of the sphere, that's proportional to the radius squared. Right? It's an area. But if you're looking out from a wire, and if you're just looking at one point, right, one circle around that wire, well, as that circle moves outwards, you're looking at the surface area of a circle, otherwise known as the circumference, and that's proportional just to r. Okay, now you can look at that area, that circumference for any circle along the wire, but it's still going to be a circle moving outwards from one point of the wire. All right, so that is shown experimentally. Let me move on to the next slide. All right, and if you want to set this equal to something, you need a proportionality constant. Now let's look at Ampere's law. Before I go back to what that proportionality is, this is Ampere's law. Now, it sounds kind of confusing. Let me read it with you and then I'll explain it. It says, along any closed path through a magnetic field, the sum of the products of the scalar component of B parallel to the path segment with the length of the segment is directly proportional to the net electric current passing through the area enclosed by the path. Right? That goes over my head too. It's like, what? Right? It's a lot easier to state it mathematically. So let's look at this again. The sum of all magnetic fields parallel to some path segment, I'm just going to write L, right, is proportional, and this is our proportionality constant. We talked about it earlier. It's the magnetic constant, or permeability of free space, which is equal to 4 pi times 10 to the minus 7 Tesla meters per amp. Okay, proportional to the current enclosed by the path. Okay, well that's mathematically, but visually, what does this look like? Let's take an example. Let's have a straight wire, and there's a current going through that wire, right? And just like on this picture here, we have a straight wire with current I. Now I can choose to apply Ampere's law for any enclosed path. If I want, I can pick a path like this, right? And I would have to add up all the magnetic field segments which are parallel to this path. It's parallel to this path, parallel to this path, and this path, and this path. I'd have to add up all of those, and then I would have to set that equal to, well, your proportionality constant times by the current inside of that path. Now, in this case, a rectangle is a very poor choice to apply Ampere's law, because the magnetic field around that wire is circular. So trying to find all the components of this magnetic field which are parallel to this, you're going to have to look at every point along that circle, break it up into components, and add the ones that are either parallel to here or here, and then find the net current enclosed by that. It's, whoa, I would never want to do that problem. I never have, never will. Why? Because there's a much better choice to be made. Just like when we choose a coordinate system, when we did forces, we choose a coordinate system to make the problem easier for us. In this case, we're going to choose a circular path. Okay, so here's our circular path. It's this green path on the diagram with radius r. And now if we apply Ampere's law, we can figure out, well, all the magnetic fields that are parallel to that path, well, all of them are, right? At any point along the circle, the magnetic field is parallel to that point on the circle. Awesome. So we're just going to add up all magnetic fields along that circle. How do you do that? Well, take B and multiply that by the entire circumference of the circle. So B times 2 pi r equals mu naught times the current enclosed. Now, the current enclosed will be the current going through the wire, because a path goes around the wire. So the current enclosed is just I. And then we can rearrange that equation to get this. B equals proportionality constant times by I over 2 pi r. So if we go back to experimentally, this works with our theoretical value with Ampere's law, right? It's definitely proportional to I and inversely proportional to r. And our constant is simply mu naught over 2 pi. That's our proportionality constant. And this works for any straight current carrying conductor. Now, I'm not going to ask you to start from this equation. Okay, I'll never ask you to apply Ampere's law. What we're doing with it in this lesson is we're using it to derive two formulas. One, the current around a straight current carrying conductor, the magnetic field around a straight current carrying conductor. It's a lot of words. And then we're also going to do, because we learned about another scenario where we have a solenoid and there's a magnetic field through the center. We're also going to apply Ampere's law later in this PowerPoint, in this lesson, to figure out the equation that we can use to find the strength of the magnetic field through that solenoid. Okay, but let's try an example. Now this example is on the back of your handout. It's example number 1. I don't need to erase that. Okay, and you're just going to find the magnetic field strength 20 centimeters. So R is going to be 20 centimeters, but make it meters, so 0.2 meters, from a long straight conductor with a current of 60 amps flowing through it. We don't even need to rearrange this equation. So make sure you can plug everything in. Wow, something interesting happened to my PowerPoint. But once you plug everything in, you're going to get 6.0 times 10 to the minus 5 Teslas. Okay? Now there's an interesting application of this. It's called coaxial cables. If you have any straight wire next to another wire, well, the currents can be going in the same direction or in opposite directions, and they're going to have magnetic fields around those wires. And so those wires will interact due to their magnetic fields. They're either going to attract or they're going to repel. sometimes you don't want your wires attracting or repelling to other wires, so we have something called a coaxial cable. And in a coaxial cable, you have the current going through one wire and then coming back outside of this insulating area, coming back from this sort of braid, metallic braid, and then you have another insulating area. But if you were to apply Ampere's law outside that entire wire, remember you have to take the sum of the current going inside of your path. Now current is a vector, so taking the sum of those two currents, which are identical in magnitude but opposite in direction, the sum will be 0. So in this case, a coaxial cable does not have a magnetic field strength occurring outside of the wire. Okay, now that's pretty cool. Moving on, we're going to apply this for Ampere's law for a solenoid. Now a solenoid, let's say we have a solenoid that goes like this. Let me explain the diagram that you're using. Okay, so the current could come out of the board at one loop, right, like this, and then go in at another, out, in, out, in, out, in, out, in, out, in, and so on. So this is our loop, right? It's going like this. That's our solenoid. Okay, which means we have a magnetic field. If you wanted to figure this out, right, you can take your fingers, and if it's coming out here and going in here, well, your thumb points in the direction of the field. So we have a magnetic field going in this direction. Okay? And outside of the solenoid, the magnetic field is 0. What would be a good shape to apply Ampere's law? Well, I don't really want to do a circle. I want something that's perfectly parallel to these lines. So let's choose a rectangle. Right? And I don't really want a rectangle around the whole thing, because right? Then my net current is going to add up to 0 again. That doesn't help me. So I'm going to choose something like this. Like that. Now to apply Ampere's law, right, we need to take the sum of all magnetic fields along the path, which are parallel. Now obviously this path and this path, right, even if these magnetic fields extend outwards a bit, they're not going to be parallel to that path. They're perpendicular, so that's 0. Outside this path, there is no magnetic field. So that's also going to be 0. The only path we care about is this one. So summing up all the magnetic field lines is just B times the entire length of that path. Well, what is the length of that path? Well, we'll choose a path that's exactly the length of the solenoid. Makes sense. Okay, so L will be the length of our solenoid. And so adding up all the magnetic fields parallel to our path segment, we get B times capital L, where L is the length of the solenoid. All right, now we need to add up all currents. Well, we have a current here, I. And we have I again. Then it's going through again. Then it's going through again. All right, so the current I goes through our path segment that we've chosen n times, where n is the number of loops that you have in our path segment. So we have to write the sum of all current is n times I, where I is the current flowing through our wires, and n is the number of loops in our solenoid. And then, of course, we have our permeability of your space. Rearranging for B, we get our equation to help us find the magnitude of the magnetic field strength inside of a solenoid. B equals mu naught times by Ni over L. Okay. And if we look at our next problem, question number 2, again, we don't need to rearrange this one. Okay? It simply says, what is the magnetic field strength in the core of a solenoid 5 centimeters long, so our length 0.05 meters, with 300 turns, that's the number of loops, and a current of 10 amps. So again, we're kind of just doing plug and play here. Right? You get 0.075 teslas, or 7.5 times 10 to the minus 2 teslas. All right. Moving on. So we had a definition for current. We said the current is the amount of charge that moves through some cross-sectional area in a wire in some time. And so you would write the units as an amp equals a coulomb per second. But here's a problem. What's the definition of a coulomb? A coulomb is an amp times a second. Okay, well, what's the definition of a current? Well, coulomb per second. And a coulomb, an amp second. Can you see the problem here? It's like looking up a word in a dictionary that points to another word. And then this word, when you look up this one, points back to this one. You can't have that. So we need to do something about this definition, for one of them anyways. So let's look at this problem. Now I mentioned it before, and I usually do this as a demo, but I'll put a video, because I found a video, another MIT video, that will actually show these wires attract or repel. Okay, so here's the problem. We have two wires. Let's make them parallel to start, with a current going through them of I1 and I2. So this one has a current of I1, and this one has a current of I2. Just like your diagram there. Well, this one, I1 has a current, and if we follow its magnetic field, it goes in the board here and out here. In here, out here. In, out, and in. It has a magnetic field going into the board where I2 is. Now, what did we learn before? We learned that if we place a current-carrying conductor in a magnetic field, it will feel a force. Okay, well, how are we going to solve this problem? This is going into the board. Okay. Now on the picture on the computer, you kind of have the currents coming out of the board. So my picture is a little different. We'll look at the one that I'm doing here, and you can apply the same thing to the one on the PowerPoint. So this is going into the board. Let's use our right-hand rule, right? Remember, this is force, this is magnetic field, and your thumb is current. So I'm going to put my thumb up, and my magnetic field is pointing in. So it's going to feel a force towards the other wire. There's your magnetic force. And you could do the same thing to figure out what the magnetic field of B2 is, and therefore the force that I1 will feel. And it will also, if you redo what we just did, feel a force pointing inwards. So these two wires get attracted. Now, if we're to figure out the actual magnitude of this, or come up with an equation, right, we can take Ampere's law, which we just solved for, to figure out the magnitude of B1, which is right here. B1 equals mu naught times I1 over 2 pi d, where d is going to be the separation between the two wires. Right? That's where we want to figure out the magnetic field strength is. Now, if we go back and use this bill, which is rearranged, where the force on a current-carrying conductor in a magnetic field equals that magnetic field times its current times the length of the wire. So this is going to be B1, because that's the field that's inside of I2, times the length of that wire. Rearranging, we write force per length. We're just going to do a ratio of the force per unit length of any part of that wire equals I2B. And we're going to substitute the magnitude of that B from Ampere's law. When we do that, we get this equation. That the force per unit length on wire 2 is equal to our permeability of free space times the current in both wires divided by 2 pi times the distance between the wires. Okay. And again, you can try this yourself, but if you make the current in each wire going in the opposite direction, test it. Use your first and second right-hand rules to figure out that the forces would actually cause those two wires to repel. All right, take a moment, pause the video, test it yourself. All right, moving on, let's say we take this equation and we're going to substitute a current of exactly 1 amp into both wires and make the wires exactly 1 meter apart. If we do that, we get a force of 2 times 10 to the minus 7 newtons per meter. we can use this to come up with a new definition for current, where current, or 1 amp, is the current in each of two long straight parallel conductors 1 meter apart in a vacuum when the magnetic force between them is 2 times 10 to the minus 7 newtons per meter. So that is the proper definition of current. Now that we have that definition of current, we can easily say, yeah, 1 coulomb is the charge transported by a current of 1 amp in a second. Now our two definitions don't cause a never-ending loop. All right. Now let's go back to that equation. We're going to do the third problem. Now the third problem says we have two parallel straight conductors 5 meters long, 12 centimeters apart. Okay, so 5 meters long, 12 centimeters apart, are to have equal currents. So I1 equals I2. So let's just call them I. And that'll give us I times I, which is I squared. For some reason, a lot of students write 2I. It's like, oh, what? No, I times I is I squared. The force each conductor experiences is here, 2 times 10 to the minus 2 newtons. What's the current in each conductor? All right, so if we rearrange, well, let's just first write this as U naught I squared over 2 pi d. We can rearrange for I squared to be our force times 2 pi d all over mu naught L. Then we plug everything in, take the square root, and we can figure out our current to be 49 amps. All right, so that's it for that lesson. Okay, but I am going to post a couple videos that I'd also like you to see. One of them is showing the demo, and one of them, now that hopefully we all understand or try to visualize electric and magnetic fields, I'm going to post a video to show you how a simple circuit works, how a simple circuit actually moves the energy towards its light bulb. We'll use a flashlight. All right.